Okay, what happens is generally your power is generated at one point and you want to move it to some other point. Okay, so the second reason the AC current is preferred is this thing we're going to look at called transformers. And so basically we're going to talk a lot about power. And if you remember, power delivered, you can write it in kind of different ways, but power delivered by something is I times V. So it's the voltage times the current. And so what you can do is when you're delivering the power, you can sort of take the same energy, power is energy per time, and you can either have it really high current with lower voltage or higher voltage and lower current. All right, and what happens is that our house, we prefer low voltages, right, because of this, right? Now, when we transfer the power over a power line, we prefer high voltages and low current because that loses less of the power. And so you sort of have this problem, and transformers are a solution to this problem. All right, and so it's another application of Faraday's law. So it's something that we totally use Faraday's law for. Here's my dated picture of a transformer. And so this is a key, I would say a key to our modern electrical systems. So starting with 120 volts, you can produce arbitrarily small voltages or large voltages, and it's like nearly 100% efficient. And so you can basically, what transformers do is they take extremely high voltage a source and then near your house and transform it to 120 volts to use in your house. Where again, if they transferred it at the 120 volts, you would lose a lot of power. And so the way these things kind of work is, here's sort of a picture of this phenomenon called mutual inductance. And so if you have two coils, okay, and so imagine you have an AC generator going through, this is just a solenoid, it's like two solenoids, and so it's pumping current through this thing, and since it's an AC generator, it's constantly changing sort of its positives and negatives, again, 60 times per second. Okay, so switching back and forth, back and forth. So the magnetic flux through here is constantly changing. All right, and so you have this because there's a current here and it's going backwards, and so a solenoid makes a magnetic field, so it's constantly changing its flux back and forth. And this flux goes over here into what we call the secondary coil, and it induces, okay, again, according to Faraday's law, EMF over here, which you can read as a current or as a voltage. And so that's the idea of a transformer. So you're using this, again, idea of Faraday's law. And so here's how typically the pictures will look like. And so you're going to have the primary, which would be here, and the secondary, and you have a piece of iron. And what that iron does is it's just the kind of material that sort of makes sure that it redirects the magnetic field. So you have this, so here you've got your primary source, and it's going to be an AC, sort of like a generated, something like we just were talking about. And so it's a current going here that's changing back and forth. And so what happens is you create this magnetic flux, okay, changing magnetic flux, and the iron sort of works to sort of redeliver it over here. And so you basically have the same flux over here as you do over there. And by changing the number of these coils, okay, you can change the different voltages you get. And so you can think about it as the voltage of the primary, by Faraday's law, is basically the number of primary loops times the change in flux. And the voltage of the secondary is the same thing, but with the number of secondary loops. And the idea here is that the flux through this iron, the change in the magnetic flux, okay, we should make sure these are all changes in magnetic flux, is the same. And so you get this relationship that Vs over Vp equals Ns over Np. Okay? And so this is sort of the key equation. So I'll write this over here just so we have this down somewhere. Or maybe not. Yeah, sorry, I won't. There's no chalk. All right. But that's the relationship that we're looking at. So you want to write this down somewhere because we're going to use this for a little bit. Okay, these two relationships are the same. And the thing is the energy, or sort of the power that you're using here will be the same. So by energy conservation, the I times the V at the primary is the same as at the secondary. So basically, you can have a high voltage and a low current, or vice versa, when you switch these things. And so let's try one of these things here. So here's an example of something that might happen like this. So the good news is you're going to France. The bad news is that France, the outlets have 240 volts. And so what you usually will buy, okay, at like the store or something, is a transformer that converts this, which you could also, if you were really into it, try to create your own. And so you remember from physics that you need a transformer. So you wrap 100 turns around the primary. How many turns should you wrap around the secondary if you need 120 volts out to run your hair dryer? So let's talk about this one and see what you think. So I think that's most everybody, and I do believe I agree with the majority, so that's great. So again, the way you would look at this is our relationship. And so in this case, you're trying to find NS, the number of secondary. And so you can plug it in. And so for us, 100 was the number of loops for the primary, and then the difference in the voltage is 120 and 240, and so you'd want to put 50 in that secondary. Okay, again, the idea here that this resistor is your hair dryer, and you want to get the sort of similar voltages to that. Okay, so let's call time on that one. And then here is another one. So now you're doing the same thing. We're using a 12-volt battery like we might have used a couple weeks ago. Okay, and so in this transformer here. And so what is the voltage across the secondary after the battery has been connected for a little bit? So you cool up your battery and you sort of let it do what it does. Maybe take a couple seconds, and then you want to measure the voltage over the secondary at that point. So what's going to happen in that case? Okay, and so I think we've got sort of two big lines of discussion here. So B and D. And so let's look at this here. So I'm going to say 0. So let's think of this. Why did I say 0? Anybody want to tell me why I said 0? Yeah. Because so we said there's no change in the flux. So it's really important here that the whole idea behind this is that voltage has to be AC. It has to be switching. All right? When the voltage is switching, the magnetic flux is constantly changing. If you have just a regular 12-volt battery, what happens is when you plug it in there, it makes a current, which creates a magnetic field, but that magnetic field is static. It's not changing. Okay? And so this, again, is sort of the one of the rationale for why AC is more useful for us is that we can use it with a transformer, where DC you can't. It just makes, and so in this case here, it would just do nothing at all. There'd be a 0 voltage there. All right. And so here's sort of the explanation of that. So the 12-volt battery is connected to a transformer, but basically there's no, transformers depend on a change in flux, so they only work for alternating currents. And so here we have 2 of them. So 2 ideal transformers are connected. A voltage source supplies a 60 hertz sinusoidal voltage with a maximum of 10 volts. What is the maximum current passing through the 100 ohm resistor on our diagram? So let's think about this one here. And so let's look at this one. So what you've got here is you've got 2 transformers. So you got a transformer here where this is, again, 5 loops and 10 loops, and then 5 loops and 10 loops. And so if we go back to our equation that we were dealing with, this equation, that again, back over here. So this guy right here, so Vs equals Vp Ns over Np. And so that's our general one that tells you and so you're going to have the voltage of the secondary equals the voltage of the primary times Ns over Np. And so our initial voltage here was said to be 10 volts. So we'd have 10 volts, then Ns over Np would be 10 over 5. So we get 20 volts. And so with this particular gale, so again, we're starting here at 10 volts, And at this in-between point, we've got 20 volts now. And the thing is this one here is just like a mirror image of this one. And so what this is going to do is it's going to step up the voltage, just like that last one, to 40 volts. So the voltage working across this resistor will be 40 volts. And so we just go back to Ohm's law to do V divided by R, and we get 40 volts divided by 100 ohm resistor, and that leads us to 0.4 amps for the current in that particular one right there. So the idea is that when you have two of these, you just work it as one, do the first one, and then basically use that to sort of figure out what the next second one would be. All right, and so here, let's do this one. So the same picture, and so compare the power supplied by the voltage source to the power dissipated in the resistor. Which one of the following statements is correct? So we're delivering a certain amount of power at the beginning point. We want to know is how much power is used up in that resistor. So maybe it's your hairdryer or a light bulb or whatever it might be in the second case. And let's just for kicks, we'll assume that we have an ideal transformer, okay? And so I agree with the majority here. So the other idea with these things, so again, we're assuming an ideal transformer, but the sort of the picture here is that the power delivered is I times V. And so that's going to be the same on both sides of this transformer. Again, it's one of the positive aspects of the transformer is that it's super efficient. So it's as close to 100% as you can get. And so you don't lose anything, you don't lose energy in this process. Okay. All right, so I think we'll go ahead and stop there. I'll be down here if you have more questions, and we'll see you on Wednesday.